You'll recognize this circuit as a half-wave controlled rectifier circuit featuring an SCR. We have a 120 volt RMS source, we have the SCR, we have a control mechanism to control the firing of the SCR, we have this what looks like a voltage source but is actually where we set the phase, so we'll go from 0 to 180 degrees with this particular control, or set point if you will. We also have an inductor and a resistor. We have some instrumentation consisting of a voltmeter to measure the source voltage. We have a voltmeter to measure the voltage on the cathode of the SCR, and we have a current meter to measure the current going through our load resistor. As we begin the simulation, we'll set our inductance to a very low value, such that it's basically non-existent. This is the result. We see the current going to our load is 0 until we fire the SCR at 90 degrees. At that point, it immediately jumps up to about 7 amps and then naturally decays and essentially turns off when the voltage reaches 0. We could call this natural commutation, as the SCR turns off when the voltage drop across it goes to 0. Something I'd like to point out, you'll notice that the source voltage, which is in green, and the blue voltage are the same from 90 degrees to 180 degrees. That's important because that means the SCR is conducting and there's a very low voltage drop across it. We can go back into our circuit and see how changing the phase angle changes the display on our oscilloscope. Here we set the phase angle to 0 and we get the expected result. This is what an uncontrolled rectifier would look like. Our current is a half sinusoid that starts at 0 degrees and ends at 180 degrees. We can then set it to 45. We can set it to 90. We can set it to 135. And finally, just to see what happens, we can set it to 180, and we'll see that the SCR never turns on. For the remainder of the lab, we're going to set the phase angle to 90 degrees. Now we can go back and we can change the value of our inductor. Previously, the inductor was so small it may as well have been non-existent. At this point, we're going to set it to a moderate range of 50 millihenries. And this is the result. You'll notice that the current, instead of being spiky, it's now rather smooth, which is to be expected because that's what the inductors do. You'll have a lagging current. Here the current starts at 90 degrees, smoothly rises to a peak of about 4.5 amps, and then decays back to 0. What's interesting is that current exists after the point at which we would have expected the SCR to turn off. You recall, at this point right here, when source voltage is 0 is where the resistor circuit turned off. But not so. We still have positive current after this point. What we're seeing is with the inductor in the circuit, the SCR continues to be turned on even though the source voltage has gone negative. It's still a form of natural commutation. We just have to wait for the energy in the inductor to dissipate before the SCR will turn off. This circuit response with that inductance is going to have some interesting implications as we continue on to more complicated circuits.